Okay, well, thank you all so much for your patience in getting started here. I'd like to talk to you today about cracking the case of ice shelf fracture. And I want to begin by acknowledging that this work is done with lots of collaborators who have helped out and provided insights and done lots of field work and just done all sorts of great things for this work. And I can't understate how important they are. I'm going to read their names. So there's Seth Olinger, Ash Morris, Maureen Denol, Rick Astor, Doug Wiens, the whole Ross Ice Shelf Vibes team, Catherine Walker, Oliver Marsh, Brendan Crowell. And these are just the people who have been co-authors on paper. So of course, there's other people we've had great discussions with and maybe published data sets that we built off of. So I just have to start out by acknowledging all of these great people that we've been working with. I'm going to start this discussion of ice shelf fractures, speaking about the history of glacier fracture and the study of glacier fracture in general, which really began by studying crevasses. And for the vast majority of people that ever encounter a fracture in a glacier in real life, they'll encounter a crevasse on a glacier, and they usually just seem like impediments to travel, and nothing else, nothing more than that. You know, you try not to fall on them, try to keep away from them. But really, there's been this wonderful history of studying crevassing in glaciology that I'd like to share with the audience. And I guess the interesting thing is that, you know, there's more to crevassing than just being these things you need to hike around when you're on a glacier. And this really became more apparent, I guess, kind of more recently in the last few decades, specifically as we started to worry about the marine ice sheet instability and about ice shelves, and about these enormous fractures that form in ice shelves called rifts. Rifts are just fractures that cut all the way through an ice shelf, whereas any fracture that doesn't cut all the way through an ice shelf is just called a crevasse. And I might also say that use the word crack or fracture. Crack and fracture are basically the same things, and crevasses and rifts are types of cracks or fractures. So hopefully that clears up a little bit to let you know at least what I'm going to talk about. And then when we say that something calved, so that rift in the last picture eventually made this big iceberg. It calved this big iceberg, which is to say that there was a mechanical separation of a big chunk of ice from the Antarctic ice sheet. This is iceberg A68. It was about 150 kilometers long. It subsequently is broken into more pieces. It was, I think, the 6th largest iceberg ever to form. And so this process of the ice sheet losing mass, of calving ice, is very closely related to these fracturing processes, crevasse formation and rift propagation. And I'd like to speak a little bit about the history of where these models come from, and I think it'll provide more insight into what we've been working on more recently. So the study of crevasses and glaciers really began in kind of the modern sense with this wonderful publication by Nye in 1955, proposing what's subsequently called, he didn't use these words, a zero stress model, which is to say that crevasses propagate to the depth where the ice overburden pressure equals the tensile stress. This diagram is actually from Weertman 73, because Nye's original paper was about 6 paragraphs or 8 paragraphs long or something. It didn't have any figures. So it took another couple decades to get to this point. And then the next major improvement to this model of just saying, you know, crevasses are just the stress equalizer, was to consider the role of water in crevasses, which subsequently is, in kind of more recent years, has taken on significant new importance. This introduction of thinking about water-filled crevasses, that you might also call hydraulic fractures, although we really only call them hydraulic fractures when we think the water is important. Just having some water that's passive usually doesn't qualify you as a hydraulic fracture. Anyways, thinking about water and hydraulic fractures didn't really begin until about nearly 2 full decades after Nye's original paper in the Journal of Glaciology. The part of the history of fracture mechanics that I would particularly draw your attention to, though, begins with a paper by Smith in 1976, also in Journal of Glaciology, which is, as far as I can tell, the first use of linear elastic fracture mechanics in glaciology. And this is going to be the method that I subsequently have used quite a bit, and is going to be a major part of the later part of the talk. And so it's worth spending a little bit more time to say exactly what this means. So fracture mechanics in general, not just the linear elastic kind, has to do with the fundamental principle that fracture growth occurs because potential energy is converted into surface energy. So when you open up a new fracture, you make more surface, you make cracked surface area, and that surface has surface energy. Where did that energy come from? It came from relieving some sort of potential energy, such as elastic strain energy, if it's an elastic material. So the way that I like to think about this is these red lines were initially straight, they're on an elastic sheet, and we introduced a little cut. So, we apply tension, we pull the sheet taut, we introduce a small crack of length A, and that relieves stress over some area, right? When you cut it, it detensions some of the material, and the area that becomes detensioned is proportional to the area squared. It's shown here in this little kind of standard diagram showing a blue triangle. A corollary of this basic principle is that unstable fracture growth, so fracture growth that occurs rapidly, that accelerates up to kind of inertial speeds, occurs when the rate of potential energy release exceeds the rate of surface energy consumption. So when you start detensioning faster than you're held back by the energy required to create surface energy, that's when cracks propagate really quickly. This is often plotted in a diagram that looks like this. And since we just made this argument, in fact, that the surface area, the surface area just has to do, you can think about it as equivalently as the energy required to break bonds to open up the fracture, to break atomic bonds to open up the fracture. This scales linearly with crack length, but the energy that is detensioned or goes away from potential energy is a quadratic function. And so there's a change in slope. You go from consuming energy to releasing energy as cracks reach a certain critical length. And this is going to be really important. We'll see this come up again and again. So again, to emphasize the difference, that previous slide was good for any material that has a fracture in it. Now we're specifically thinking about elastic materials because we get some more interesting analytical tools, and also it describes a broad class of fractures. So the fundamental principle of linear elastic fracture mechanics, as distinct from fracture mechanics in general, and I'll point out, as was originally proposed by Irwin in 1957, who was cited by Smith in 1976 in the Journal of Glaciology. The fundamental principle now is that unstable fracture growth occurs when a quantity called the stress intensity factor, which is a property of fractures in elastic materials, itself a function of the fracture configuration and loading, when this key value called the stress intensity factor exceeds a critical value, then unstable crack growth begins. It turns out that critical value is itself a material property called the fracture toughness. So we know that the fracture toughness of ice takes on a particular range of values, and we can ask the question, given a particular crack and a particular set of loadings, we can calculate a stress intensity factor and determine whether the fracture will propagate based on the fracture toughness of ice. So this diagram that we drew previously, the specialization to an elastic material is simply that this change from consuming energy to releasing energy, where unstable crack growth begins, occurs at this critical value of the stress intensity factor, commonly written K sub 1 for mode 1 fractures, equal to the fracture and toughness K1C. So that's basically the end of the super technical details, and I think that hopefully this will be interesting to people who have thought a little bit about fractures. And if you haven't, I think the key ideas should still permeate the rest of the talk in a way that will be available to all. So I'll just highlight a few more things in the history of glaciology and glacier fracture research to get us to where we are today, which is a great pair of papers by Kees van der Veen in 1998, which is still linear elastic fracture mechanics, but presents significant improvements. So this work generalized the work by Smith in a number of ways. So it was the first study to show that fracture toughness actually may limit propagation in glaciers, that the reason why crevasses extend to a certain depth is because they only have enough stress to generate a certain stress intensity factor, which does not exceed the fracture toughness. and so that can actually be a constraint on the depth extent of crevasses, was first proposed by Van der Veen. He also examines vertical propagation and vertical propagation paths rather than just a final state, considers both surface and bottom crevasses with and without water, and finally considers a finite thickness glacier. Actually, all previous studies had implicitly assumed that you don't need to worry about how thick the glacier is, but that's not always the case. And what we're showing here is sort of a typical result, which is the stress intensity factor plotted as a function of the depth of a crevasse. So you see that the two solid vertical lines are values of fracture toughness. I only labeled the one on the right. And so basically the crevasse is expected to grow to a depth, this is for a surface crevasse, is expected to grow to a depth where the solid curve intersects one of the vertical dashed lines. That is where the stress intensity factor equals the fracture toughness. And so that first happens at a point where the, I guess I should say, unstable fracture growth basically begins at a depth of about, a height above the base of about 60 meters. Okay, so the last point on my timeline that I would like to tell in this telling of the history of glacier fracture studies, and I appreciate that there may be other tellings of these stories, and I'd be happy to hear other people's narratives as well, is really a seminal event, which is the collapse of the Larsen B ice shelf. And this just was, in terms of the number of papers about fracturing in ice shelves, after this point, there's just so much interesting literature that I can no longer pretend that it falls along a simple linear historical narrative. There's a lot of different research directions, and I'm going to build on some of them, but I don't unfortunately have time in this talk to talk about all the interesting things that people have been doing since that time. And right, the reason why we care, why Larsen B was so important, is because it just provided unambiguous evidence that ice shelves provide buttressing support to the grounded part of marine ice sheets. And that as a result of that, ice shelf fracture and ice shelf breakup can actually destabilize the ice sheets and result in the ice sheets losing mass to the ocean. This is a more recent study by Rod et al. In 2018. Line A and B are basically so we're looking in a transect across Crane Glacier, which is one of the glaciers that fed into the Larsen B ice shelf. And A and B were the velocity profile before breakup, and C, D, E, and F are the profiles afterwards. So a little bit of interannual variation after the breakup, but you can see it went from about 1.5 meters per day flow speeds to about 5 meters per day. So factor of 3.5 speed up. And this is important. You know, I think it's broadly appreciated these days that one of the ways that you can get large amounts of ice loss in Antarctica is by destroying ice shelves, by having ice shelves fracture and fall apart. So with that, I will call this the summary of the historical context for this work. And I'll just summarize it in 2 points to say that linear elastic fracture mechanics provides a useful approach to understand glacier fracture propagation, and that ice shelf fracture is connected to a more broader sense of ice sheet stability because ice shelves themselves buttress inland ice. So the question that I would pose at this juncture is, how does the unique glaciological setting of ice shelves modify fracture propagation? So what is special about crevasses in ice shelves? What is special about rifts in ice shelves? And I'll focus your attention on several processes that we'll talk about, including buttressing stresses, flexure, interaction with ocean swell, and the behavior of ice cliffs. And with that, I will jump right in. So I'm going to start describing my own work now in describing what is, to my knowledge, the first 3-dimensional study of ice shelf rifts. So this is a fully 3-dimensional description of a through-cutting fracture in a simple rectangular shaped ice shelf. Although this is the first 3-dimensional study, it of course builds on numerous wonderful previous studies, including those by Eric Leroy, Christina Holm, Christine Platt, Leverman, Chris Borstadt. So there's been a lot of work on fractures in ice shelves and on rifts in ice shelves. And I'll hopefully explain to you some ways in which our model is slightly different or provides a slightly different perspective. So as I said before, the model is fully three-dimensional with no approximations to the stress tensor beyond linearity. Loading is from gravity. The ice fronts have a water pressure load, which ends up being a springy kind of boundary condition. And deformations are measured relative to a hydrostatically pre-stressed state. If any of those points interest you, they're described in more detail in this paper in the cryosphere. And the basic behavior of the model that comes out of applying these boundary conditions is that the top of the ice shelf basically flexes in along the rift. This is actually a well-known phenomenon in ice shelf glaciology. The imbalance in the forces between the water pressure applied by the ocean onto the ice and the ice overburden pressure, which is deeper with depth and in the opposite direction, act to create a net moment on the ice front. This tends to result in top-out rotation, and we see that in our simple finite element solutions of rifts, that the rifts themselves behave as sort of tiny little ice fronts. And this has the interesting effect that the top of the rift actually becomes stabilized if it goes into a state of partial contact. The two walls tend to push together because of this moment, and that actually can stabilize rift propagation. In the bottom right-hand corner here, I've shown a diagram actually plotting the stress intensity factors that we calculate, and you can see that the top of the rift has a lower stress intensity factor than the bottom of the rift, which is consistent with the top of the rift being in partial contact, that extra force making it more difficult to fracture that part of the rift. I'll add as an aside that the main technical conclusion of this modeling is that we develop a parameterization of this flexural effect in rift propagation. And in that way, we can parameterize flexure into simpler two-dimensional models, which are much easier to carry out. Meshing is just horrible in three-dimensional finite element models. And so it's far simpler to run 2D models than to run 3D models. We next look at the impact of boundary conditions on the ice shelf. So I've drawn here two simple cartoonish ice shelves, one which is basically an ice tongue, and one which is confined within an embayment. And the main difference between these two is that buttressing stresses along the walls of the embayment can slow down the ice in the margins. We look in detail at the question of how does buttressing stress affect rift propagation. So we know from the observations following Larsen B that when buttressing stresses are removed, the ice accelerates. But now we're asking the question, if the buttressing stresses are removed, what does that do to the fractures? And so to examine this, we look at rifts that are either in the middle of the ice shelf or rifts that are in the margins of the ice shelf, the right and left column. And we look at three different types of boundary conditions. One where we have an ice tongue where there are no sidewalls. One where there are strong margins, which for an elastic material, we just take to mean zero displacement along the margins. And one with weak margins, which is a roller boundary condition. So there's free slip with zero shear traction, but zero normal displacement. And we find that the lots of buttressing can in fact drive rift propagation. Previous work, as I mentioned, has focused on the other direction, showing that when there's a loss of buttressing due to calving, there can be a resulting acceleration in ice flow. So it turns out that the arrows of causation can go both ways, and there potentially could be a feedback where loss of buttressing drives more fracturing, which in turn drives more loss of buttressing, which drives more fracturing. The specific technical details of how we determine this from linear elastic fracture mechanics is basically to look in the regimes where the fracture toughness is exceeded by the stress intensity factor. And those occur within the regions of the yellow dashed lines in these simulations. So for each of the 3 boundary condition types, and looking here just at marginal rifts, we see that there are basically 3 conditions. So for the strong margin case, the rifts become unstable only near the front. And then the weak margin case and the ice tongue case are actually very similar. They have a very different state of stress, but they both have instability occurring for the fractures in a similar region of the ice shelf. I don't know how questions are usually done in these, but I'd be happy to take a few questions now if there are questions, if anybody has some ready. And then I'll give a deliberate 15-second pause if anybody has questions in the chat or anything.
We usually collect them at the end, but if anyone wants to type into the chat, I know, having just been at a virtual meeting, that if you don't give people long enough to write at least a couple of characters in there, it won't happen. We do usually collect them to the end, though. So
okay, I'm happy to do that. So I'll just keep going. Let's see. Oh, that jumped all the way to the end of the talk. I don't know why I did that. I said the magic words, end of the talk. Okay, so the next part of the talk, the evolution of this, is that I was basically trained PhD postdoc time is doing a lot of mechanics and a lot of simulations and first principles physics. And after doing this 3-dimensional study, I was really left with the feeling that the way forward is going to be with more observations, because I just don't know what to put into the next model. And so in the next part of the talk, that's exactly what I'm going to discuss, is a set of seismological observations of ice shelf crevasse growth and ISAT-2 laser altimetric observations of ice shelf rift devolution. So the first of these 2 projects involve seismology and seismic deployment on the Ross ice shelf that observed a significant influence of ocean wave interactions with crevassing. This is a big collaboration with lots of PIs at different institutions. I came onto the project relatively late, but the project was called the Ross Ice Shelf Vibes. Vibrations of the Ross Ice Shelf, something like that. The Ross Ice Shelf seismic deployment, to my knowledge, was the most extensive in space and time ice shelf passive deployment to date. It lasted about 2 full years, and it covered the entire Ross ice shelf in a flow line and a cross flow. So looking at a single flow line in the bottom right-hand corner here, you can kind of get a sense of scale of where we're working. Obviously, DRO2 wasn't floating above the ice front. The ice extended forward since bed map 2 was made, which is why it's misplotted there. But DR10 there's higher station density there because those are right near a rift. Although in this talk, I'm mostly going to focus on the stations DR1, 2, and 3, which you can see are located right near the ice front. They're within a kilometer or so of the ice front. And these stations observe something remarkable. They observe repeated earthquakes that occur with such perfect regularity that the whole ice shelf hums. So this is just the phenomenon that if you have some beating pattern with a sound that goes dun, do, 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 eventually you can, if you blur over a long enough time window, you observe spectral peaks. You observe spectral peaks that are spaced apart in time or in frequency by exactly 1 over the recurrence time of the repeating event. And as you can see, well, the spectral peaks are shown of the data, the seismic data are shown in the upper plot, and in the lower plot, I'm showing the actual seismic data, which shows these impulsive events. And in blue, and in the gray line, I'm showing the ocean swell, as also inferred from a seismometer, this time in what we call the swell band of about 0.03 to 0.12 hertz, so around 10 seconds. And what we see is that although it's not perfect, the repeat frequency of these events is locked to the tide, is locked to the swell. That for about every ocean wave that passes by, we get one ice quake. Not all waves, ocean swell waves, generate an ice quake, and the phase between the two can be somewhat scrambled at times, but it's coherent enough to still form these spectral peaks. And so it's quite regular over periods of kind of minutes to hours. There are a few remarkable properties of these ice quakes triggered by ocean swell. They exhibit thresholding and hysteresis. So on both of these plots, the vertical axis is the energy in the swell band, and the horizontal axis is the energy in the ice quake band. And so I'll draw your attention to the left figure first, and we see that as the swell energy increases, we only get a gradual increase of high frequency energy and of the ice quake energy until we reach a certain threshold, at which point the ice quake energy takes off. So after we cross this threshold, it appears that the ice quakes begin to act. And similarly, when the swell goes away, the ice quakes actually stick around for a while, and they keep happening at lower swell levels since they've already begun. So there's thus providing a sense of hysteresis. We model these effects of using both swell and flexure to explain the observations. We have a simple model with a crevasse. We treat surface crevasses and bottom crevasses, and we treat the boundary conditions that give rise to flexure at the ice front, like in the Niels Ree paper that I showed earlier on in the talk. And a few main processes become evident. So focusing our attention just on the top panel, when the ocean swell acts on the crevasses, at least two different things happen. One is that the ocean swell changes the compressional boundary condition at the front of the ice shelf. And this stress change is actually transmitted over long distances in the ice shelf. So that's shown schematically here with the water with the big arrow and the ice with the small arrow, showing the perturbation because the wave crest is drawn as being at its peak there. Then there's also a remote loading that happens as the wave propagates into the ice shelf and causes small amounts of tension and flexure as it propagates through the ice shelf. So both of these two effects give rise to the total swell effect on the crevasses. Then the effect of flexure is more simple. If you have top-out rotation that stretches the top of the ice shelf, it puts the top of the ice shelf into tension and it favors crevasse growth on the top. It puts the bottom of the ice shelf in compression, and it suppresses crevasse growth at the bottom. And we're working on extending this to sort of Till Wagner's model of the footloose mechanism, where wave erosion can actually give the opposite sense of flexure at the front. We haven't quite done it yet, but I would generally expect the pattern there to be the opposite of this, that you would expect compression on the top and tension on the bottom. I won't get into too much heavy lifting of the details of how the model behaves, but it's really fascinating. The ice front is a wonderfully rich region to study, even in relatively simple models. There's basically the horizontal axes on both of these plots is the distance from the ice front. So, and it's on a logarithmic scale to illustrate the different scales that are operating. The vertical axes on both plots are the stress intensity factors, so the propensity of fractures to propagate. And the left figure is looking at surface crevasses, and the right one is looking at bottom crevasses. So if we just look at surface crevasses for the time being on the panel A, the asymptote at large distances from the ice front, greater than that vertical dashed line labeled x equals lambda fg, that's the flexural gravity wavelength. So at distances greater than the flexural gravity wavelength, you no longer feel that you're near the ice front, and those horizontal dashed lines actually correspond to the solutions of Van der Veen from 1998. But then the Van der Veen solutions no longer hold in the region near the ice front, where flexure stretches the top of the ice shelf and compresses the bottom of the ice shelf. That's the red dashed line. There's actually not a simple analytical solution for the mode 2 case, the yellow line. The solutions are then further modified as you move to within one ice thickness of the ice front and also to within the draft of the ice front. Each of these scales actually presents its own boundary layer solution. We haven't gone into all the details because I'm not sure that they're all completely relevant to the problem, but or that there would be that much more to learn from having a simple parameterization. But over most of the region where crevassing is really prominent, the flexural solution is probably reasonably accurate. So we can move on and further discuss the impact of ocean swell. And what I'm showing here, the black solid lines are the same as the previous slide. So they are the stress intensity factors that account for bending. And then the gray shaded region occurs due to ocean swell. So it shows a range over a full wave cycle. So during part of the wave cycle, fracture is favored, and during part of the wave cycle, fracture is inhibited. So the conclusions from this modeling regarding the observations are that, first of all, the hysteresis and thresholding are natural consequences of a basic fracture model because they're exactly described by conditions such as the stress intensity factor exceeding the fracture toughness. The location of the swell-induced events is also naturally comes out of the model because it turns out, and as we see in these figures, the effect of ocean swell is amplified by flexure. So swell by itself can favor fracture growth, crevasse growth in part of the ice shelf, but that effect is greatly amplified when you include the effect of flexure. It's actually a nonlinear effect because you're changing the moment that's applied at the ice front when the swell wave crashes into it. So this amplification actually means that flexure and swell together amplify and destabilize fractures more than either would independently. To speak a little bit more about the seismic wave propagation and to highlight work of Seth Ollinger, Seth has gone into quite a lot of detail to model wave propagation in ice shelves. And it turns out that seismic waves in ice shelves are different than seismic waves on land because at low frequencies, the waves that we observe essentially behave like ocean swell. They behave as surface gravity waves in arbitrary depth water. And then as you move to higher frequency, they behave more like seismic waves. So Seth has an open source model that's available on GitHub. And so if you have some neat ice quakes on ice quake data from ice shelves, I would highly recommend you have a look at his code. And it certainly has been critical for us to understand the details of what we're seeing in this project. To wrap things up with one last project, measurements of fracture topography with the ISAT-2 laser altimeter. This is work in collaboration with Ash Morris, Catherine Walker, and Oliver Marsh, and has really benefited from all of the interactions with the ISAT-2 science team. So ISAT-2 is a satellite laser altimeter, which means that it measures, it uses a laser to measure reflected photons that come back from the surface of the Earth, from the surface of glaciers, and with some clever processing can be used to create digital elevation maps. We're mostly going to use the along track products, ATL06 for the aficionados, and the data at this level of processing basically look like they do on the left. These are just color-coded by the meters above sea level of a given point along track. And you can see the dark band that goes from lower left to upper right in this figure is a region of low topography, which is in fact an ice shelf rift. And it is in fact the ice shelf rift that's pictured on the right, called the Halloween crack. The brave souls pictured in the picture on the right are from the British Antarctic Survey. I like to think it's our collaborator from BASS, Ollie Marsh, but I'm actually not sure if that's a picture of Ollie or if he took it or if he was even there that day. But the front ice shelf and the Halloween crack in particular is just a great place to go to study the fracture mechanics of rift propagation, specifically because of the extensive and long-running field program maintained by the British Antarctic Survey. We just have so much data there that we can ask questions that we can't ask anywhere else. And the ISAT-2 observations just highlight the Halloween crack really well. It stands out quite nicely. Although it turns out that building a robust detector to pick these out of the data in an automated fashion is highly non-trivial. And that's been the work of Ash Morris. He kindly provided this figure, and you can see on the right the optical imagery showing the presence of the rift tip at the Halloween crack, and on the left, the ISAT-2 data showing the exact location and the exact topography surrounding the rift. So when we run this rift detector, we can make a map of the points that are detected, which are shown as tiny red dots in the map on the left. The colorful squares are GPS instruments, which we'll compare to in a minute. And one thing that we see right away that's interesting is that, you know, at first we were getting these double detections where it looked like there were two parallel rifts right next to each other. And so we asked Ollie about this, since he's been there and looked at it with his own eyes. And it turns out that we're probably seeing actual melange blocks. These parallel detections right next to each other are probably just the same rift with a block of melange in the middle, such as is shown in the figure on the right. To give a sense of scale, that the rift and the figure on the right is probably 500 meters wide. To speak again to the field program run by BASS, we have highly informative and really useful GPS data. So we can just plot the difference between two stations. We can also be a little bit more clever and do a 4-station version of the same calculation. But for simplicity, we just consider, you know, what is the relative displacement between two stations on opposite sides of the rift. So we fit a straight line to these data, and we come up with a number of about 300, or a number of about 300 meters per year, a little bit more, and over about a year and a half of observations. That gives us a total opening of about 600 meters if we assume it all happened on the rift. And it turns out that the rift opened a lot more than that. So I'll state the observation again, just because it's so puzzling. So you have two GPS stations, and they measured that the rift should open at about 300 meters per year. But then when we look in the altimetry, we see that the rift walls are moving apart by a rate more like 600 meters per year. And again, actually being on the ground and using information from, in this case, aerial photographs, we deduced that the reason why the two measurements seem to disagree is in fact because there is mechanical erosion of the rift walls. And so I've just highlighted a few points here in the foreground of this oblique image that show blocks detaching from the rift walls and falling into the rift. This actually isn't the Halloween crack, it's the North Rift, a rift called the North Rift, which is right next door to the Halloween crack. And so we basically hypothesized that the difference in these two rates, the spreading rate between the two GPSs and the rate that the rift walls are moving apart, is actually due to a combination of stretching plus the actual mechanical erosion of the rift walls. To be controversial, you know, we could ask, is this the marine ice cliff instability of Passes and Walker? And I don't think it is. It's not, because the ice isn't thick enough. You know, the marine ice cliff instability with capital letters is applicable to much thicker ice than what we see here. But then it's interesting that we actually see a significant amount of rift wall erosion at a much lower threshold than predicted by Passes and Walker. And I think some of those clues to why that would be the case, why we would have so much rift wall erosion, is actually probably to be found in the crevasse model I presented in the previous section, although we haven't used it for that purpose yet. So at this point, I've been talking for about 45 minutes, and so I'll wrap things up. And again, return to this question that's been driving this research project. How does the unique glaciological setting of ice shelves modify fracture propagation? Basically come up with 4 answers to that question so far, 4 lines of inquiry that were motivated by this question. So we found that ice shelf rift propagation can be stabilized when strong buttressing is present. We found that ocean swell and flexure enhance crevasse growth. we found that seismic waves can actually be quite useful in tracking ice shelf fracture. And we found that ice cliff failure occurs over recently formed rift walls, and that this has a complicated and not immediately obvious relationship with the marine ice cliff instability. I'll add the final comment that all of the code associated with this work is available on GitHub, and all the data are available in FAIR compliant open repositories, NSIDC and IRIS for the seismic data. So with that, I would thank you for listening, and I'd be happy to entertain any questions or comments that you might have.
Thank you very much indeed, Brad. I have to say that's the first time I've ever heard anyone singing seismic signals. Very impressive.
One of my specialties.
So as usual, if people want to indicate on the chat if they've got questions. Julian, do you want to unmute yourself?
Sure. Hi, Bradley. Thanks for your talk. If you could go back to that that slide where you had the wave movement expanding the fissure. It was a way back.
This one? Or
No, further. Yeah,
one?
that one. Yeah. So you were talking about tension and compression. And later in the Halloween crack, you were talking about, mechanical processes also being at play. I was wondering, do you think also mechanical processes could be here as well in terms of attrition, maybe like scree or detrital grains that help to erode the fissure itself?
Yes, and I think there's so much to say. We started with linear elastic fracture mechanics, which is, ice is just an elastic block of material, but really it's obviously so much more than that. And so the interaction with the surface processes is really interesting. With, we say that rifts are filled with melange. That's how we refer to the material inside of the rift, and the melange itself consists of a mixture, surprise, of sea ice, of broken off blocks, but also of windblown snow, of just accumulation, and all these things together, combine to create this complicated material that I think does have a significant impact on the actual fracture stability. Does that answer your question?
Yeah, I can see what you mean for the for the Halloween crack, yes, too. So I see what you mean here. Okay. Thank you.
Thanks. Olga.
Very nice talk, Brad. Thank you. So I have quite a few, but I'll try to limit them. So since we are staying on this slide, if you compute the extra stresses caused by flexure or flexural gravity waves, they're quite small. They're something order of like 10, 15 kilopascal. So do you have a sense or a comment how important those are to crevasses and development of fractures and cracks and whatnot?
Yeah, I guess my comment would just be that, and I think you may be familiar with this already, but for the sake of everybody involved, the key idea of the stress intensity factor is that fracture doesn't occur at a particular level of stress, because stress is a tensor, it's complicated. Which stress would it be? Would it be the normal stress or the Mises stress? There's one of the invariants. It could be a lot of different things. Instead, the idea of the fracture toughness is that of the stress intensity factor is that it depends on both the stress and on the geometrical configuration. And so specifically for like a toy problem of a crack in a hole space, the stress intensity factor scales like the stress times the square root of the fracture length. And so even very low stresses can cause fracture if the fractures are very long. So this is one of the key ideas of linear elastic fracture mechanics, that longer fractures are more unstable than shorter ones. And so for the rifts in particular, the dimensions can be quite long, and so they're actually can be susceptible to small changes in stress. For the crevasses, obviously the key dimension is, the dimension of propagation. Vertical, the lengths are much smaller, but it could still be the case that small stresses can give rise to propagation. And I think there's a few unresolved parts of tying the model to the seismic data, but I think the compelling thing I would come back to is really the observation that even if the LEFM model isn't perfect and there's other processes at play, the observation is quite compelling that there is a high frequency event almost every swell cycle during periods of high swell. And I think the most obvious explanation for that is that there is tiny amounts of crevasse propagation, tiny amounts of fracture growth that are occurring during each swell cycle.
Well, somewhat provocative comment then to that. How come we still have ice shelves? Swells exist all the time, and nevertheless we still have ice shelves, right?
That's a great question. Well, that's exactly something I've asked that question many times. I think there's a lot of different answers. So one really compelling observation that we're working on right now is that the North Crack on Brunt formed almost parallel to the Halloween crack. And that's really weird. So this would be like if you have a fracture in your windshield screen on your car and another, a rock bounces off the road and creates a new fracture, and the new fracture propagates, 1 centimeter away from the old one for the entire length of the fracture. It's hard to imagine why that would happen unless the first rift had basically completely rehealed. And so this idea that melange can stabilize and strengthen rifts is something that's been in the literature recently. Eric Leroy just had a paper in the Proceedings of National Academy about this. I think that could be part of the story, but then on Brunt, calving still happened anyways, even though the first rift healed up. So that might be part of the answer. It might delay calving, but I don't think it's the whole answer. Another thing is just in our study, rifts are only unstable when they're connected to a source of shear, like shear margins. And when rifts were in the middle of the ice shelf, they were all stable. And so there's this idea that you have a window of time when you can form a rift that can give rise to calving. So on the Ross Ice Shelf, on the Crary Ice Rise, you have huge amounts of shear. The ice is moving quite fast and really being ripped apart, and there's some deep rifts that form. Then they all get advected out into the middle of the ice shelf, so they don't have time to, they're no longer connected to a source of shear, and so they can't propagate. I think that's a major stabilizing effect for rifts.
If I may, one other question, and it's on the other part for flexure at the front about your boundary layers and that part of the talk. No, I think the next one, when you, yeah, that's great. So what you're showing here is that you have high stresses and large intensity factors quite close to the calving front. But if I understand correctly, we still have large tabular icebergs. So how come the majority of calving happens via large tabular icebergs? So I'm thinking about Ross Ice Shelf or Filchneroni or even Emery, the big ones. How come we do not have the majority of calving happening on the spatial scales, what you're showing here, something like few, maybe up to 10 ice thicknesses on flexural, on the distance of the flexure, characteristic flexural distance?
That's a great question. So just to put one point on what you said, the Ross is really unique in its wave environment, to my knowledge. So not all ice shelves, actually, most ice shelves have never had a seismic deployment, but of the ones that we've seen, none of them have nearly as much wave activity as Ross, because Ross is just open to the South Pacific. And so you can get storm tracks, you can get waves from Alaska on the Ross Ice Shelf. It's really incredible. And none of the other ice shelves really have a geometry that quite favors that in the same way. But to your point about why ice shelves exist, and why do we get tabular icebergs if the ice shelves should be so susceptible to wave-induced fracture? I would say that the values I've plotted here are only for a particular depth of crevasse. So I think what we're seeing is that we're just dancing around the stable point of the crevasse at some given depth. That at some given depth, there's a depth that the crevasse would propagate to in the absence of any ocean swell activity. And then what we see in the observations, this thresholding in hysteresis, is that the waves have to be a certain size in order to trigger the event, to get a little pop that extends the crevasse. But then the hysteresis kind of tends to show that there is actually a healing process, that the rift actually, the fracture actually returns back to its initial state. So it could actually just be these kind of repeated earthquakes are not contributing to a net growth of the crevasses.
Thank you.
Yep.
Laurie, I think, has a question. Laurie Padman.
Yeah, just following on with the front rifts for a second. Putting a real number on the swell that creates them, what sort of amplitude are we talking about?
Oh, that's a good question. So I would refer you, Peter Bermirsky has a nice series of papers about the wave environment around Ross. And I would really go to his papers to be sure about this, but my sense is that having swell amplitudes in the meter range of, one to several meters, I'll leave it kind of ambiguous, but in that kind of range is typical during the big winter storms on Ross.
During the winter storms, but then have a lot of
austral, northern hemisphere winter.
Okay.
Yeah.
Because most of the year on the Ross, you have so much sea ice out the front that's damping the energy out.
Yeah, and really the big storm months on Ross are like January, February, but really February, March, April is when we see the biggest storms. And my understanding is that a lot of these, I know I saw Doug McHale on here a minute ago. He worked on this problem a while back. I think a lot of the storms actually originate, some of them are kind of local in the Southern Ocean, but many of them are even in the Northern Hemisphere.
Okay, so my real question was about the ice cliff erosion in the rifts.
Yeah.
And you sounded like you're a little surprised by the fact that this occurs, that they're occurring without enough, well, you tell me. What, are you surprised that they occur?
I didn't expect it would be this big of an effect. I didn't expect that it would be a third to a half of the propagation. Because, I mean, I think our simplest model of ice cliff stability, or there are probably others, but the one I'm familiar with, the Walker and Jeremy Bass's model, is, it predicts cliff erosion at fracturing of the ice cliff erosion, whatever you want to call it, at much greater thicknesses. And so I think that there's maybe, so their approach was not based in linear elastic fracture mechanics, it was kind of based in compressional failure on shear faults. And so maybe there's more to it than that. I do think that, the type of approach that we've taken could be used to dig into that in a little bit more detail, but we're not quite there yet. We just haven't gotten to it yet.
Could it be as simple as that there's residual damage from the initial rift, so that the strength of the ice within some distance of the visible rift is already weakened?
I potentially, I'm not sure. That would be really interesting to consider. Yeah, I have some ideas about some seismic observations. Seismic waves can be really sensitive to damage. They can be highly sensitive to kind of parts per 10,000 of seismic wave speed change. And so I think that there could possibly be some way to test that. I'm not sure what the answer is. It could be that there's damage, it looks pretty intact to me, but it's all covered in snow, so it's hard to say. I think that it'd be interesting to actually do seismic tomography and see what the damage evolution is like. It's an interesting idea.
Okay, thanks.
No, thank you.
Roger, I think you had a question.
Yeah, thanks very much, and thanks for the talk, Brad. The lovely slide we were looking at for quite a lot of the questions earlier on, with essentially a 1D model of the flexing in some parts. Lovely. That's the one. Smashing. That illustrates the issue very nicely, but obviously the front of that particular ice shelf is curved. So I was wondering what your thoughts are on how the ice shelf responds more in 2D than in plan view.
Oh.
The analogy I'm thinking of is in earthquake seismology. We've got the Rayleigh and Love modes, and when they, for example, run into a sedimentary basin, that they can come in from different directions. They can reflect, and you get this kind of egg box pattern of nodes and antinodes. The classic being, the Mexico City earthquakes, where you get patches of the city that are completely destroyed, and then 100 meters away there's people who didn't even know there'd been an earthquake because of the interference of the surface wave coming from different directions. So just wondering, what kind of thoughts there were about these models and these interactions more in plan view from a curved ice shelf front.
Yes, I mean, that's totally the direction. That's a great direction to go in. And that's not what here. We just have a simple model of wave propagation. It's just a 2D cross section. But to your point about Rayleigh wave interactions in sedimentary basins, there's a seismologist down the hall from me at University of Washington here, Maureen Denault, works on exactly this, and amplification in sedimentary basins, including Mexico City. The problem for the ice shelves has been addressed. Actually, Olga has worked on this a bit, and actually looked at how the real geometry of the ice shelves, the Ross ice shelf, can focus flexural gravity waves. And I know that right now the group at Stanford, Eric Dunham's group, has a paper that's a preprint that also looks at flexural gravity waves with realistic geometry, and it's complicated. So the group at Stanford's working on the transient response, so actually looking at a single individual wave, how does it scatter and diffract and propagate around in the ice shelf, and it is quite complicated, but I think it's still tractable, and in fact it might give us a better representation of what the actual wave stresses are. That's a topic that we've written a few papers about so far at this point, but there still remains a lot to do, and I think these cutting edge numerical simulations are going to be quite useful that are being developed, but we haven't quite incorporated them all the way yet. But I do think it's a good point. It's a good direction to be thinking about. Thank you.
Yeah, and I guess nobody's going to go and put a dense seismic network across the entire of the Ross ice shelf the way they did with US array moving across the USA. So to get the field data. Smashing.
Well,
thanks very much.
Yeah, the answer to that, I think, is going to lie in fiber optic seismology, which I'm actually really excited about. So we've recently at the University of Washington secured a few distributed acoustic sensing interrogators, and we have plans in the works to actually do large scale deployments on glaciers and ice sheets using these interrogators. So potentially sidestepping the issue, because you're totally right that a US array would be really difficult to maintain and deploy on an ice shelf like Ross, but it'd be a lot easier if you could do it with a fiber optic cable. Yeah,
that's great. I mean, DAS is a great way forward. We've got a cable and interrogator system here at the University of Leeds, and we're competing with each other for ways of using it. So yeah, good stuff. Thanks very much.
I think I actually got a discount from the manufacturer because I referred you guys to them.
I'll pass on that and let the relevant person take the percentage. Cheers. Thank you.
Brilliant. Are there any last questions for Brad? There's none on Facebook, and I think we've probably run out of questions here. So what I'm going to do is just share the slide for next week's seminar, which hopefully you can all see now. Next week we've got Oh no, it hasn't quite come up yet. I have to press the share button. So,
Sorry, it's I closed it.
so next week we have a full team from Aberystwyth to talk to us about Himalayan debris covered glaciers. So Bryn Hubbard, Katie Miles, Duncan Quincy, and Anne Rowan. So hopefully see you all next week. Hopefully you got to see the slide there. It's a little bit hard for me to sometimes see what's being shared, but hopefully it's the title slide for next week. And hope to see everyone next week. And thank you very much indeed again, Brad. So that was really fantastic seminar. So yeah, exactly. Thank you very much and see you next time.